A PV module in SPICE or in ngSPICE should have an IV characteristic like this. Further, one should be able to define this point, the short circuit point ISC, and also the VOC point. Now these two parameters we should be able to define for the PV module model which is in SPICE. Then only we will be able to perform the simulation of interfacing power converters with PV module and further check whether maximum power point tracking is occurring for various different types of modules. PV arrays are different IV characteristics having different short circuit and different VOC points. Remember that the short circuit point ISC, this point, this ISC is directly a measure of the insolation, and therefore definition of this point in SPICE would mean that you are able to also control the value according to insolation. So it is important that we have some measure of control in deciding what ISC should be for the PV panel and also VOC. Therefore, we need to have in the SPICE, ngSPICE, a source called PV source, which is having a symbol like this and a characteristic, the IV characteristic like this, which the PV source should be able to emulate. And such a source having this IV characteristic, we will call it as PV source. We need to do two things. One is to write a subcircuit, and this subcircuit model should represent the PV source having this kind of an IV characteristic. So we can use the current source diode model for writing the subcircuit model. In fact, we can leave out the R shunt and R series and have an idealized diode and current source model itself. That should be sufficient. And second, we have to make this symbol so that you can call it in the schematic editor. And let us say that we write the symbol in a file called pvsource.swym. So these two aspects we need to do. Then we will have the model of PV source, and then we can use this model of the PV source as a component within the SPICE and along with all other components, for example the components in the DC-DC converter, and simulate the entire system. Now let us first generate the PV source model. Recall that we had discussed this model of the PV cell consists of the current source, the diode, the R shunt and the R series. RS and R shunt are non-idealities. We can dispense with them, and then to make the model simple, we will try to use only what is essential, most essential, the current source and the diode. And let us build a model along this line with the modified, simplified circuit. So let us have a current source and let us have a diode. And the current source will have a constant value, and we have the terminal with the terminal voltage VT, and we have IT, the terminal current here, and this is what we need to determine. The current source value, we'll set it as a constant, and we'll set it proportional to insolation, which is ISC value. Now for this Let us write down the model. IT, which is what we want, equal to ISC minus the diode current value will be IT. And what is the diode current value? It is as given here. So I naught, reverse saturation current, into exponential VT, terminal voltage, divided by N VT. This VT is the voltage equivalent of temperature, minus 1. So this value, N is 2 for silicon and VT is 0.026 for 25 degree Celsius. So I will take it as a value equal to approximately 2 into 0.025 is equal to 0.05 for easy calculation, and rewrite our IT model as ISC minus I naught e to the power of VT by 0.05 minus 1. So this will be the model of this simplified PV cell or PV module. Here you see that IC is a value, ISC, the short circuit current, is a value that we can set. So that is settable, and we can adjust that for module to module. What about VOC? We will see how we will adjust for VOC too. But first, this model, how will you implement it in the subcircuit? So within the subcircuit, we will use what is called as a B source. ngSpice provides a nonlinear source called the B source. Go to the ngSpice user manual and refer to the syntax on B source. It's a nonlinear dependent source. It is between a plus node and the minus node. You can give either a expression for current or expression for voltage, like this. B1, 0 to 1 is the node, I is the current expression, and goes like this. You can also give a conditional statement within here. So let us try to use the B source model into our PV source module. So we will use the B source between NA to NB, and let me call it as BPV. It is between nodes NA and NB, and let us have a current output I. Normally the current output is positive, considered positive for a source when it is entering the positive node, and negative and leaving the positive node. And in our case it is to leave the positive node, and therefore I will indicate it as a minus of something, some expression which will come in here. What is the expression that will come in here? It will be IT, this expression for IT that we have written. We can introduce one more point at this stage of the modeling. We don't want negative current to sink into the PV cell. When IT goes negative, that is reverses direction, we just want to not allow that. So set IT to 0 during those times. So which means only when IT is greater than 0, then allow IT as calculated by this equation, or else make IT, this current I, equal to 0. So this is the conditional, inline conditional statement that ngSpice allows, and we can use this equation in our subcircuit model. Next comes the point on how to adjust the voltage of the PV module. Can I increase the voltage of the PV module? Now let us say here in this point of the equation, I divide by a V scale value. Now let us say, for example, when V scale was not there, VT terminal voltage was around 0.7 to 0.8. Now if I make V scale as a value 10, then for the same amount of diode current to flow, this numerator here should be around 0.7 to 0.8, which means VT should go to 7 or 8. 7 or 8 divided by 10 will be 0.7 to 0.8. Therefore, automatically, because this is the current source, automatically to achieve the same current levels, Vt will automatically scale to a higher voltage of 7 to 8 volt if we make V scale 10. If you make V scale for any other arbitrary integer value or non-integer value greater than 0, Vt will accordingly scale such that this numerator will be around 0.7 to 0.8. So therefore we can get a voltage scaling also by adjusting this value. So V scale and ISC will be the two parameter values that we will adjust. Now let us try to build the subcircuit and see how we incorporate that into the SPICE schematic. I have created here a folder called PV module, and within that folder I have three files. One is pv.cir file. You are familiar with what's a CIR file. There is a schematic file and then pv.sub file, but I will first look at this pv.sub file where we have placed the subcircuit. So if you recall, we had a pv.sub file, subcircuit file earlier, which had only the model of the diode. Now I have included this part, the PV source. So the subcircuit or the PV source is as follows. It has two terminals, the positive terminal, negative terminal. I am passing two parameters, default value of ISC set to 1, voltage scaling factor set to 50. And the first part here, setting the ISC value. So I am opening a voltage source between NSC and 0, two nodes, and then passing this ISC parameter here. So I will have a node voltage value of ISC. Likewise, I will have a node voltage value of V scale, decoupled independent nodes, and then I will use that later in this model here. Now observe, this is the BPV model between 1 and 2 of the terminals. I am setting it as minus. Now this is our IT equation. VNSC is the node voltage here, which represents ISC. ISC value minus 1e minus 7. This is I naught. E to the power of V12 is Vt divided by 0.05 for NVT. I have also divided by V and DV, the V scale value. Now if these values, if this IT value is greater than 0, then pick the value of IT as calculated, or else if the IT value is turning negative, clip it to 0. So this is the model of the PV source that we will be using, which has both ISC and voltage scalable, adjustable, and which is what we need. Now we have the model, we need a symbol which will call this model. So let us now create the symbol. Before I start creating the PV module symbol, would like to show you on the browser. If you put in the keywords like GEDA symbol creation wiki, you will have a lot of search outputs. GEDA GAF symbol creation, the wiki of the GEDA project, and that is a good point for you to read and get the steps on making symbols. Another point of entry for you to learn more is this creating your own symbols in GShem by Ashwit. This is also a good place for you to start. So read up on this and see how the symbols are created. Okay, now we will go to making our PV source symbol. Open GEDA schematic, opens up like that. And for symbol creation, you need to remove all these, delete them, and the extension .sch, make it as .sym. So you save as, so I'll just say pv source.sym, and then let us store it. Here. So now we have pv source.sym. Now very important for you to note is here you see at the bottom grid 100 you have to keep the grid at 100 and 100, but you can improve the resolution at the time of drawing, but at the time of saving always keep this at 100 and make the resolution like this bigger. You can always change this by going to options, scale up grid spacing, scale down grid spacing. Use that one to adjust the grid spacing here. And use this add net, add bus, add attribute, add text, add component. These are the things that you will be using. Add pin. Okay, so I can add a pin, okay, and place it like that. Okay, that is a pin. Now when I double click on the pin, you will see that the properties coming in: pin type unknown, pin label, pin number, pin sequence. You need to give the proper attributes here. Pin number and pin sequence, these can be different, but most of the time they are same, but pin number sometimes can be different from the pin sequence. Pin sequence is the sequence that you will use in subcircuit. So this is associated with the subcircuit sequence. Pin number here is associated more with the IC package details. So that is very important for you to provide. So I have added one pin here, another pin here. Now if I double click, you see that I have given pin number 1, pin sequence 1, common sequence. You can give a pin label, it can be alphanumeric, I can say it is plus. Pin type power. So these are the attributes that I am giving to this pin. You see the other pin, pin number 2 with sequence 2, it's a minus label, and again a power pin. Now I have added this by going to add attribute. So go to add attribute, you can choose refdes value, so for this particular label. So I have added this refdes and given x PV question mark. This question mark can be, if you are having many PV sources within a schematic, you may want to name it as 1, 2, 3, 4. So add that question mark x, because I am going to refer it to a subcircuit, and therefore for subcircuit the first letter should be x, like that. Now we need to draw the symbol. So take the add line and let me make the drawing like this. Make the drawing such that it represents a PV source like that. Save it in between. So after having completed the drawing, look at all the labels. This label plus, minus, power, everything shows up. It is too noisy, and this is this is the value. So in the value, I am calling PV source subcircuit, passing ISC value and Vscale value. This is important. So what you can do is mask everything. Let there be just the pin and this XPV. Then it looks neat. So if you use EN, then everything disappears. There, it is hidden. Save. Now don't just quit. Go to edit, select all. This is a very, very important step if you want to get your graphics right when you are doing the layout, so that when you are wiring the circuit diagram, they should lock to the pins, the wires. So select all and then go to symbol translate. Very important step. Every edit you do that, symbol translate to 0. Okay, that's it. Now you save. After this process, you can close it. Every time you edit the symbol, do the select all, symbol translate. Okay, so I have saved it into where? You see, in your local home directory, you will have a GAF folder when you install GEDA. Inside the GAF folder, there is symbols. And inside the symbols, you can have your own library of components. So I have created some components. I will share them with you, the resources. So within that, I have created PV source. There are various other things also which I will share, and you can look at them in leisure. So the PV source, this is what we created. So I will put it back. So this is created, placed in this place. But you have to tell GEDA GSHM to look at this place. Where do you tell to look at this place? So in your user home, Control H, you will unhide the dot files. So .geda configuration file, go in. There is a GAF RC file. If it is not there, create one empty GAF RC file, and inside that, if I double click, you have to type this component dash library dash search within double quotes /home in your local home directory. GAF is the directory where you place this folder, symbols folder. Within that, it will search for all the folders and separate libraries, component libraries that you have created. So this search path is needed, then it will recognize and it will put it up. So let us now look whether it is going to look for our symbol that we have created and see if we can simulate this. Next, I open the pv.sch. We create the schematic. We go into the schematic, and then here we shall place the components. Let me go into the component library. I have placed it in a components. Now let me look down and see if PV source is popping up. You see PV source is popping up that we just now created. I will place it here. I will take that, close this. I will also take a sine source, place this here, and then let me make the connections. Let me edit the label. Let me edit the value parameters. I will make the ISC short circuit current as 10 amps and voltage scale as 50. I have here included pv.sub, that file, which contains the subcircuit. So you see that pv.sub is containing the subcircuit, which is called by the pv.schematic. Within pv.schematic, we have the symbol, and this symbol is calling the PV source subcircuit file, which is residing here. So all are connected well. So that's it. Now we can simulate in ngSpice. Now I will open pv.cir. So pv.cir performs these operations. .tran between from 0 to 5 milliseconds, 0.01 millisecond as the print output using initial conditions. It will include pv.net, which we need to generate. We will generate that. Then there is a set of dot control statements. I would like the plots to be on a white background and black foreground, so you can do that. We have done this earlier. Run the command, then plot. What do you want to plot? So you see that I will reduce this so that you can see what we are doing. So plot IVSC, the current through this output source, versus VNV, versus the terminal voltage. Then VNV, the terminal voltage, into the current through that is the power, divided by 40 versus the voltage. So we are actually seeing the IV and the PV curve. Why did I do divide by 40? So that both can be clearly visible on the same screen. You see that if I am setting this at ISC 10 amps and approximately 40 volts for the VOC, you will see that it's around 400 watts. So or less than 400 watts, because it is 70% of VOC into ISC. And that divided by 40 will be around 10. So this is kind of a normalized so that we can see both on the same screen, but mentally you multiply by this value, whatever you see on the plot out, to get the actual power. So now let us plot this and then see. I will close this and then open the terminal window. So we will go to the folder. Now, so first generate the netlist, gnetlist, all these commands /out pv.net, pv.sch. We have seen this command before when we did pSpice experiments. So let us do that, and then ngSpice pv.cir. So it will run, execute, and it will plot this. You see it has plotted this, and as expected, short circuit current 10 and open circuit voltage around 46. And see, current doesn't go negative. Beyond that, current becomes 0 because we have set a clipper limit for IT going negative. So that is advantageous, and this blue line is the power curve. Of course, you can try for various combinations. What we have now achieved is that we are able to have a PV source symbol where I can scale the value of ISC and VOC, and the same symbol you can use it for any PV application, and it gives you a curve, almost the IV curve, like an expected photovoltaic cell characteristic, as against the original model where we used the diode and current sources and kept on putting them in series and parallel. So a huge number of components you will have to include, and for every different specification you will have to keep changing the set of PV cells in series and parallel, and keep adjusting them, which can lead to not only mistakes but a huge PV source circuit and number of components, which will slow down the simulation. This is very elegant. You don't have to do anything. Whichever be the experiment that you want to simulate, you just have to give the ISC, the short circuit current value or the insulation value, and the voltage scaling factor, and you are done. You have a PV source. We will use this PV source to simulate our MPPT tracking with DC-DC converters. So before we put in the MPPT algorithms, we need to first see if our PV source, when interfaced with a DC-DC converter, works well.